To install this tool, we're going to clone the repository from GitHub and follow the installation instructions in the README. The first thing we're going to do is to set up a virtual environment using Python version 3.8.5 or greater. Before we install the software, we need to activate our virtual environment. We can now follow the instructions. In this example, we're going to use a CPU install for the tool. We'll now install the additional scicpd library. We can now launch the tool from the command line. The tool presents a plain interface with the option to load data. We will download sample data into the required data structure as specified in the README. We'll be using the cancer imaging archive, and following the instructions on the README, we're going to open up the search portal and search for a specific ID that's been tested with the tool. Expanding this particular result shows there are 2 scans on 2 different dates, and expanding further gives us a number of options. For this demonstration, we'll be selecting the 1.5 I30F scans for the patient taken on 2 different dates. Going to the cart, we have the option to download. This will download a manifest file. To open this file, we will need to install the NBIA data retriever. Again, you can follow the instructions on the Cancer Imaging Archive for Windows or for Mac. Once you've installed the data retriever, opening the manifest file should open the data retriever itself. You will need to agree to the data usage policy and double check the correct number of scans are loaded before selecting a directory to download. Exploring the downloaded files, you'll see there are a number of subfolders, and the images are contained as .dcm files. However, they will need to be renamed and moved into the correct folder structure for use in the tool. You can either do this by hand or use the ctcopy bash script to do this for you. This script can run on Mac or Windows. We'll begin by copying the ctcopy script that we downloaded into a location that we can execute. And the usage is within the folder that contains the images, specify the destination folder. We'll navigate to the first set of scans. And here we can run the ctcopy script. The destination in this case will be the folder that we installed the data to, extra data, data 1, 1, abdo 1. Now repeat that process for the second set of scans. Specifying abdo 2. It's useful to have the terminal window with the tool running open in the background to check for any errors. We'll navigate to the extra data folder and highlight the first directory containing the patient number. We'll see a message that we are missing some of the transforms because we have not generated them yet. Now you can see the main layout of the tool. On the left-hand side we have the first scan and then the second scan underneath. On the right-hand side we have the overlapping unaligned images where you can see the shifted movement between the two scans. You can cycle through the different slices using the slider, and you can change the slice orientation. For some of the traditional alignment techniques, these are available within the tool itself. These may not perform particularly well, as you can see here, but we can try the phase correlation technique. Here you can see the alignment has improved. While not 100%, it is available throughout the slices of the model. There is also a 3D scan view available. To help visualize where you are in the scan. To calculate the coherent point drift transformation, again following the instructions in the README, we can run the command line instruction to generate the transform for patient 1. This is assuming you have the sample data from the previous section. This process typically takes around 45 minutes to an hour per transform. Once the model has converged or reached 1,000 iterations, it will be saved in the correct location. We can now load in the model through the graphical user interface using the sample data previously imported. You will now have access to the CPD alignment option. And a good demonstration is around the hips. So as you can see in this example, we have movement around the hips. When we apply the CPD alignment correction, we see that movement adjusted for. You also have available the CPD warp, which shows you the areas which have been warped to match. This is also available throughout the 3D scan, and you can modify the training parameters to better suit the images that you'll be using. To generate a tissue sectioning model for segmentation and lesion detection, we can use the script referenced in the README. This script must be run from the main project directory and will generate the required model in the correct location. Once this model is generated, you can access the model through the GUI tool. You'll need to load up the scan data again, and now you will be able to enable tissue sectioning to access the tissue sectioning model. This will be available throughout the slices, and the parameters can be modified in the Python script. You can select which scan to apply the segmentation to. Finally, you can detect ellipses. This is the basic lesion detection mechanism which utilizes the segmentation data. In our example here, our segmentation may be a little noisy, so we may generate more ellipses than we'd expect. Here we can see 120 ellipses or lesions were detected roughly in each scan. Obviously too many in our example, but just to walk through the visualization, for each scan, scan 1 and scan 2, you can see a lesion ID, the center location of the lesion in pixels, and the volume in pixels cubed. In this tool, a pixel is approximately 0.7 millimeters. We can try to locate visually the lesions by clicking on each one. So in this case, as we can see here, it's incorrectly identified an entire organ as a lesion. But as you experiment with the different tissue sectioning parameters, you'll be able to fine-tune this for your own purposes. Additional self-supervised and deep learning techniques for tissue sectioning are available through the experiments folders. More information is provided in the README and in the individual Python script files themselves.